Hello everyone, welcome to Calculus Lesson 8.5, Intersection of Lines and Planes. So in the last lesson in 8.4, we looked at possible ways that two lines can intersect in R2 and R3, or 2 and 3 dimensions respectively. Now we're going to look at how those same lines intersect with planes. Now since we're dealing with lines and planes, that means we're automatically dealing in R3. All right, so when a line intersects with a plane, there are three possible cases that you can end up with. And I'm sure you can probably kind of visualize this yourself. Grab a piece of paper, grab a pen or a pencil, and just think of the different ways that they could intersect, all of the unique possible ways. Okay, so the first way that they can intersect, imagine you have a plane. Now the plane, remember, we always label with a pi and a subscript. So this might be the plane pi 1. And if a line intersects this plane, maybe that line is called L1. Okay, so one way that it can intersect is just at a point. Okay, so something like this. So there's L1. Okay, so we would say that this line and this plane, they intersect. And that means that there is one solution. So what we're interested in is how to name it and how many solutions there are going to be. Let me just draw two more planes for the other two cases. So there's pi 1 again and pi 1 again. Okay, so in the second case, we're going to just take that line and place it on the plane itself. Okay, so there's L1 right on the plane. So this is the case where we say that the line and the plane are coincident. Now, here's where it can get a little bit tricky with the terminology. You might want to say that that is parallel. And it's really tempting to say that L1 is parallel to pi 1 because, after all, there's going to be some direction vector along pi 1 that is also a scalar multiple of L1. And so that gets a little bit tricky. So a way in which you can say it is it's parallel and coincident. But if you were to just pick one term to describe these two interacting with each other, it is coincident. And in this case, we have infinitely many solutions. Now, the last case is quite literally you have L1 parallel to pi 1. Okay, so it never touches it, it never interacts. So parallel. Now, another way to determine, or rather express this situation, is to say that the line and the plane are parallel and distinct. Okay, or parallel and not coincident. And in this case, we have 0 solutions. Okay, so those other names that I just mentioned, I just want to stick them here as well so you have them. So sometimes you can say that this one in the middle is parallel and coincident. And this one on the right here, we can say it's parallel and distinct. If you just say parallel, it means this. If you just say coincident, it means this. All right, or you could say parallel and not coincident. All right, so any of those. All right, so let's jump into an example. So example 1. All right, determine if the line and plane intersect. And then once we do that, we need to determine the solution. All right, so let's do part A first. So part A, we've got the plane pi 1, and pi 1 is given by the scalar equation 9x plus 13y minus 2z equals to 29. And the line is going to be L1, and it's given by the parametric equations x is equal to 5 plus 2t, y is equal to negative 5 minus 5t, and z is equal to 2 plus 3t. All right, so t is an element of the real numbers, so that is something that we know at this point, that's a parameter. All right, so determine if they intersect. So they're either going to intersect like this. Now, here's the thing. If they intersect, they're going to intersect at a point. If they intersect in this case, then you have infinitely many solutions. And if it's like this, well, they're not intersecting at all. Now, anytime let's just look at the left case here. Anytime a line intersects with a plane, you're going to be able to find some kind of point of intersection, whether it's case 1 or case 2. In this case, all of the points on the line match a point on the plane. But in this case, 1 point on the line matches 1 point on the plane. Now think back to when you would try to find a point of intersection of 2 lines. What would you do? Well, you would take y1 of line 1 and y2 of line 2, and you would set them equal to each other and solve for the x value that would allow those two to be equivalent. Okay, so we're going to do something similar here. If these two intersect, then that means the x value of the line has to match the x value of the plane at that particular point. And I know that the x values on the line are represented with this parametric equation, 5 plus 2t. So what I'm going to do is stick that in for x, and I'm going to stick the y is equal to negative 5 minus 5t in for y, and 2 plus 3t in for z. And if I can come up with some t value that makes left side equal right side, that means I have found a point of intersection. And in fact, solving the problem like the way I just explained, it will allow us to determine whether there is one point of intersection, infinite points of intersection, or no points of intersection. So all in all, in example 1, we're going to have parts A, B, and C, and you're going to have a chance to see all of these cases. Right, so one by one. So let's start off with part A. So let's go ahead and plug x into x, y into y, and z into z. So working with the equation of the plane, so we have 9x plus 13y minus 2z equals 29. All right, so now time to plug in the values. So 9x, I'm just going to leave empty brackets for now. 13y minus 2z equals 29. All right, so in place there, I'm going to stick in 5 plus 2t for the y, negative 5 minus 5t, and then for the z, 2 plus 3t. I just have to expand the values at this point. All right, 9 times 5 is 45. 9 times 2 is 18. So that's 18t. 13 times 5, so break that up into 10 and 3. 10 times 5 is 50. 3 times 5 is 15. 50 and 15 makes 65, but accounting for that negative sign, you get minus 65. So there's that same product again. So you have minus 65t minus 4 minus 6t equals 29. All right, at this point, we're going to collect our like terms. So I've got terms with t's and I've got constant terms. All right, so let's see here. We've got, how are we going to do this? Let's do 18 minus 6 first. So 18 minus 6, that's 13. And 13, well, it's positive 13. Positive 13, negative 65. So what do we get with that? Should be minus 53. So minus 53t. Looking at the positive numbers, 45 minus 65, well, that's pretty easy. That's going to be minus 20. Negative 20 minus 24, that's going to be, or sorry, minus 4 is minus 24. There we go. Equals 29. So bring the constant over to the right. 29 plus 24 is 53. So that means we're going to have minus 53t equals 53. All right, so what's t? T is equal to negative 1. All right, so sure enough, knowing the value of t, that means that I can actually find the point of intersection simply by plugging it into x, y, and z here. But the fact that I only have solved for one possible value of t, so in other words, there's only one value of t that will make this expression here true. That means that there is only one point of intersection. So let me just make a point of that here. Since there is one solution for t, therefore one POI. That's not point of inflection like we did in integral calculus. This is point of intersection. All right. So let's actually find that point of intersection, right? That's what the problem is asking us to do. So to find that point of intersection, I'm going to plug the values into the equation for the line. So L1, all right, so x was 5 plus 2t. So that's 5 plus 2 times negative 1. All right, so that's going to be 5 minus 2, which is 3. Y is negative 5 minus 5t. So that's -5 minus 5 times -1. Lots of negatives. -5 times -1, that's +5. -5 and +5 makes 0. And last but not least, z, 2 plus 3t. So that's 2 plus 3 times -1. 3 times -1 is -3. 2 and -3 makes -1. So there it is. There's your point. 3, 0, -1. So therefore, again, make sure you're using round brackets for points, square brackets for vectors. Therefore, 3, 0, -1 is the only point of intersection of L1 and pi1. Okay, so that is it for part A. Okay, so now we're going to move on to part B. Same thing, determine if the line and the plane intersect, and then determine the solutions. Okay, so for part B, we have plane pi2, and it's given by the equation x plus 3y minus 4z equals 10. And the line L2 is given by the parametric equations x is equal to 4 plus 6t, y is equal to -7 plus 2t, and z equals 1 plus 3t. Same thing. If they're going to intersect, then that means that the x and the y and the z values have to be the same. So that's what I'm going to do. I'm going to take these parametric equations for x, y, and z and plug them into their respective spots in the equation of the plane. All right, so here we go. X plus 3y minus 4z equals 10. All right, so x, leaving empty brackets for the variables, minus 4z equals 10. All right, so x is 4 plus 6t, y is -7 plus 2t, and z is 1 plus 3t. Okay, so let's do our expansion. All right, the first set of brackets, well, we can just drop those. So 4 plus 6t, -7 times 3, that's -21. 3 times 2 is 6, so that's 6t. Minus 4 minus 12t equals 10. All right. So collect your like terms. So there are t's. 6t plus 6t is 12t. 12t minus 12t is 0t. Now, I know usually at this point you wouldn't even want to write anything. Maybe you'd want to just write 0 or nothing. But write 0t. If you have no t's, write 0t, and you'll see why in a second. All right, so we took care of the t's. Now we have 4. Let's just do it like this. 4 minus 4. 4 minus 4 is gone. And then we have -21 and 10. So if I take the -21 and bring it to the right, it'll be 10 plus 21, which is 31. All right, so I end up with the expression 0t is equal to 31. Notice that even in part A, I should have actually circled this since it's not the final answer, but you circle whatever expression or value you get for t. And the reason why I've circled this here is because I can't go any further. If you ask yourself, what value of t can you plug in here that you multiply to 0 and get 31, there is no such possible result. Okay, so since there is no possible value of t to satisfy this expression, that means that there is no point that exists that is the same to both the line and the plane. All right, so that's what we're going to say here. Since no value of t makes this statement true, therefore, there are no solutions. Okay, so remember, the only way you can have no solutions is if you are dealing with this kind of case, if it's parallel. Okay, so parallel and distinct, or you can call it parallel and not coincident. Okay. So therefore, L2 and pi2 are parallel. Hey, you could just call it parallel, but I'm just going to write parallel and distinct. Okay, so there is our result for part B. All right, so moving on to the last part of example 1. So C, we've got the plane pi3, which is 4x minus y plus 11z equals -1. And we've got the line L3, and that's given by x comma y comma z equals -2, 4, 1 plus t times 3, 1 minus 1. All right, so t is an element of the real numbers, and actually, I forgot to put that here, t is an element of the real numbers. Okay, so you got to find a point or points of intersection if it exists. All right, so the only big difference between this problem and the previous ones is that instead of being given the parametric equations, you've just been given the vector equation. So getting the parametric equations is pretty straightforward. Just break x, y, and z up into their constituent parts and their constituent equations. So what I'm going to do is I'm going to break L3 up. So we have x, y, z. Right, so x equals -2 plus 3t. Y equals 4 plus t. And z equals 1 minus t. Okay, I hope that's okay. So now going with that, we're going to plug in the x, y, and z expressions into x, y, and z in the formula for the plane. So we have 4x minus y plus 11z equals to -1. So 4x minus y plus 11z equals -1. Let's plug those expressions in. So -2 plus 3t. We have 4 plus t here and 1 minus t in the last slot. Expanding, 4 times -2, that's -8. 4 times 3 is 12, so that's plus 12t. -4 minus t plus 11 minus 11t equals -1. All right, collect your like terms. So right off the bat, I see 12t minus 1t, that's 11t. 11t minus 11t is 0t. So it's starting to look like it's turning out like the previous one, but let's keep going. -8 minus 4, that's -12. -12 plus 11, that's -1. So I have -1 plus 0t equals -1. Bring this -1 on the left to the right, so it becomes -1 plus 1, which is 0. Interesting, so we end up with 0t equals to 0. Again, ask yourself, what possible values of t will make this expression true? And when you really think about it, you can plug in any value for t there. You can plug in 6, you can plug in -7,352, whatever you want. And 0 times that number will always equal 0. So that means that any value of t makes that statement true, hence there are infinitely many solutions. So since any value of t makes this statement true, therefore there are infinitely many solutions. And I will say that pi 3 and L3 are, well, I'll just call them coincident. You can call it parallel and coincident if you'd like. Okay, so there we go. So just to summarize from example 1, the number of intersections is determined by the number of possible values for t. Very important. All right, so we are now officially 1/3 of the way through the lesson. So let's move on to a new, not necessarily a new idea, but before we move on to example 2, I want to demonstrate something. Okay, so a little bit of theory, I guess. Now, the 3 cases that we had on the first page, we can illustrate, well, I'm going to illustrate here using 2 illustrations. So go ahead on your sheet and draw the same plane twice. Okay, so we're going to label these planes the same because they are the same, pi 1. Now you know that each plane can be uniquely characterized by its normal vector. Okay, that's the vector that is 90 degrees to that plane. Right, so there's a normal vector. And in reality, you know that I can stick that normal vector anywhere on the plane as long as it's at 90 degrees. It simply tells us the orientation of that plane. Now, for the plane on the left, I'm going to draw 2 scenarios. Scenario 1, I'm going to draw my line up here. So here's L1. Now, when you're dealing with the line and a plane, the plane you know is characterized by either the normal vector or 2 non-parallel direction vectors on the plane itself, With the line, lines also have direction vectors, and this is important because it tells us which way the line is going. So, for example, for L1, maybe my direction vector is going to the right, and maybe my direction vector is going to the left, but it really doesn't matter here. The point is that if your line is parallel to the plane, notice that that direction vector, whether right or left, it's going to be always at 90 degrees to the normal vector. So that's really important. Okay? And I'll have the same circumstance if my line L1 is in the plane too, because even in this case, my direction vector, whether right or left, is going to be at 90 degrees to the normal. And of course, that normal can be up or down. It'll still be 90 degrees. And so we come to the following conclusion. If the direction vector of the line, so that's M, is perpendicular to the normal vector of the plane, which is N, then that means there is no intersection or infinite intersections, right? So not one, none or all. Now, I hope that at this point, I've drilled this into you so much that you just recognize it, that when two vectors are perpendicular, you should automatically think that, well, that means that their dot product is 0. So m dot n equals 0. That's a really important consequence. Okay? So if the dot product of the direction vector of a line and the normal vector of the plane is 0, that means they're perpendicular. Hence, either there is no intersection between them or there are infinitely many intersections. Very important. Now, the only other case you have is going to be right here where we're going to draw the line just crossing through the plane and hitting it at one point. So here's L1, and the direction vector might look something like this. And you can even see from the picture, whether you draw the direction vector down and to the right or up and to the left, it's going to be at an angle to N that is not 90 degrees. So here we're going to say if M is not perpendicular to N, then we know that the dot product between those two vectors is not 0. So therefore, there is one point of intersection, one POI. So understanding that is going to be really important for us to move on to example 2. All right, example 2. Determine if each line intersects the plane. Now, if you're reading that going, well, we just did that same question in example 1. Why did we have to learn new theory? Well, here's why. If you go back to example 1, the question says, determine if the line and plane intersect, same so far, and then determine the solution. When you need to determine the solution, that's when it's important to actually find the t-value, right? And then using that t-value, plug it back into the x, y, and z of the line, and you can figure out what the actual point of intersection is, if there is a point of intersection. In this example, we don't have to find the actual solution. We just have to determine if they intersect. And you know what? While we're at it, we'll also determine how. So determine if each line intersects the plane, and if not, how. So if there's only one case it doesn't intersect, that's when it's parallel, so we would explain that. If you don't actually have to find the point or points of intersection, then all you have to really do is investigate the relationship between the direction vector of the line and the normal vector of the plane. It's going to be much faster for you. So we're going to do that here. All right, so for part A, the line L1 is given by the vector equation R equals 2 minus 5, 3 plus S 3, 2, 1. And the plane pi1, which is 3x minus y plus z equals -6. All right. So the first thing I'm going to do is identify the direction vector of the line. So that's m. That's given by this piece right here that's attached to the parameter. Right. So there's m, and I can also determine n, right, the normal vector. I keep grabbing the green pen here. N comes from the coefficients, right, of the scalar equation of the plane. So it's going to be 3 minus 1, 1. Right. So we're going to go ahead and look at the relationship between m and n. So let's take the dot product. Either it's going to equal 0 or it's not. And then we can move on from there. So m is 3, 2, 1. And we're dotting that with 3, minus 1, 1. Okay, so you know how to do dot product at this point. Take the sum of the products of each dimension. So we're going to have 3 times 3 plus 2 times negative 1 plus 1 times 1. All right, so 3 times 3 is 9, and then we have minus 2 plus 1. Negative 2 and 1, that makes negative 1. 9 minus 1 is 8. Regardless, that does not equal 0. Therefore, m and n are not perpendicular. If they're not perpendicular, that means you have already taken out these two possible options, right? So that means that you don't have parallel, you don't have coincident, that means it's intersecting at some point. All right, so therefore, since we don't actually have to find the point of intersection, we just have to state that therefore, there is one point of intersection. Okay, so there it is for part A. Let's do another example, part B. L2 is given by the line R is equal to 1, 0, 1 plus T, negative 2, 1, negative 4. And I keep forgetting to write this. S is an element of the real numbers. T is an element of the real numbers. Okay, so there's the line. And the plane is going to be pi 2, 4x minus 2z equals 11. Same idea, we have to identify the direction vector. So the direction vector here is negative 2, 1, minus 4. So there's n, and I identify the normal vector. So that comes from here. Notice that there's no y. So if you just want to put a placeholder there, you can just call this 4x plus 0y minus 2z equals 11. Remember, you don't need all of the coefficients there to have a plane. So that means my normal vector is 4, 0, minus 2. So there are my two vectors. Let's go ahead and take their dot product. So m dot n, so we have negative 2, 1, negative 4. Dot that with 4, 0, minus 2. All right, I'm just going to go ahead and fill in these brackets first. There we go. Negative 2 times 4. And then I have 1 times 0 and negative 4 times negative 2. Oh, interesting. All right. So the 0, that just goes away. Negative 2 times 4, that's negative 8. And negative 4 times negative 2, that's positive 8. Negative 8 and positive 8 make 0. All right, since the dot product is 0, so since m dot n equals 0, therefore m is perpendicular to n. Now, if they're perpendicular, you have, well, two possible cases, right? So either you have the line that is parallel and distinct, or you have the line that is coincident. So we got to figure that out. Now, a way to figure that out is if the line is coincident, that means every single possible point on the line also exists on the plane. If it's parallel and distinct, there is no point on the line that also exists on the plane. Now, if I can find just one point on the line that also matches with the plane, I know that we are dealing with this scenario. I know that there are going to be infinitely many intersections. And I know a point on the line. It's given by this position vector right here. 1, 0, 1 means that there's a vector going from the origin to the point 1, 0, 1. All right, so I'm going to try. If that point also satisfies the plane, then we have infinitely many intersections. So let me just write that here. Check if 1, 0, 1 exists on the plane. Let me just move that up. Okay, so our equation of the plane is 4x minus 2z equals 11. So that means that the right side of this equation is equal to 11. Let's see what the left side is can equal. So left side, we've got 4x minus 2z. And let's see here. So x, so we have 1, 0, 1. So there's x, y, and z. So that's 1. Z is 1. So we have 4 minus 2, which is 2. All right, so left side does not equal right side. Since left side does not equal right side, therefore, r and pi 2 are not parallel and coincident, but rather parallel and distinct. All right, so there is the solution for part B. They are parallel and distinct. All right, so we saw that the point 101 on the line didn't exist on the plane, which means we're dealing with this scenario right here. Okay, we are now 2/3 of the way through the lesson. So let's move on to the last example, example 3. All right, find the distance between the plane 4x plus 2y plus z minus 16 is equal to 0 and each point. All right, so we're going to have two parts to this question, A and B. So in part A, we have to find the distance between this plane and the point P, which is at 10, 3, minus 8. All right. Now, the last time that you learned how to do this was in section 8.4. The very last, I guess, theory and concept shown to you in 8.4 was how to find the distance between a plane and a point. So hopefully you recall that we did use projections in order to determine that. And we're going to almost derive it from scratch again here, but it will be part of the problem-solving process and a way of showing our work. Always, always, always draw a picture. You've got a plane, so you're just drawing something that looks like a piece of paper. Okay, so if we want to call this plane pi 1, then we can label it here, pi 1. All right. Now I've got some point. I don't know where it is. Now that point might be on the plane, so don't ever disregard that possibility. That point might be on the plane. And if it is on the plane, that means that the distance is 0. So the first thing that you should always, always check is see if this point is on the plane. So first step, always check to see if the point is on the plane. All right, so here we go. So the plane is 4x plus 2y plus z minus 16 equals 0. So let's do this. So 4x plus 2y plus z minus 16. So that's the left side. And I know right side is 0. All right, so we're plugging in this point right here, 10, 3 minus 8. All right, so left side. So we have 40 plus 6 minus 8 minus 16. All right, so 46, negative 8, and negative 16 make minus 24. 46 minus 24 does not equal 0. So this does not equal 0. So therefore, the point P is not on the plane. All right, so again, first thing that we're going to check, because like I said, if it is, you're already done. All right, so we established that the point is not on the plane. That means it's somewhere around the plane. Okay, so I'm just going to draw a little dot right here and say that, well, that's where the point is. So here's P, 10, 3, minus 8. Now, what we saw in 8.4 is that if you're looking for the distance between a plane and a point, well, you can use the idea of projection. Okay, so we know that planes are uniquely characterized by their normal, right? And a normal is a vector that is perpendicular to the surface. Now, it wouldn't do me very much good to draw the normal up and perpendicular to the plane. It would do me more good to draw it down and, sorry, not parallel, perpendicular to the plane. All right, and I'm specifically going to draw the normal going to this point. I don't have to draw it going to this point. I can draw it going anywhere, but it'll help me to draw it going to this point, and you'll see why in just a moment. So there's the normal. And you don't have to draw the arrow all the way to the point, because in reality, the normal is just some vector. It may or may not have the magnitude required to get to that point. So just to keep, the case more accurate, we'll draw the arrow a little bit shorter here. All right, so what I need to have some other vector that when projected onto the normal, I can figure out the length of that vector such that the length represents the distance between the plane and the point. So what I'm overall trying to do here, and again, this is 90 degrees, I'm trying to find this distance right here. So we'll call that D. Okay, we're trying to find D here. Now, if I take some vector and I project it onto N, I can find the magnitude of that, and that magnitude will be D. Now, the key to that is the vector that I project onto the normal, it has to have one point at P, and it has to have another point on the plane. Okay, so since I need one point P and one point on the plane, why don't we just call the other point Q? And I don't know exactly where that point's going to be, but let's just stick it here. I need some point on the plane. And you know what? You can figure out points on the plane. I have the equation right here. If you had the equation of a straight line and you needed to know a point on the line, you could just plug in any value for x within the domain and see what value of y gets spit out, and that would be a point on the line. So same thing here, except instead of x and y, we have x, y, z. So plug in an xy pair or an xz pair or a yz pair, plug in two of them, and figure out what the third is equal to. All right, so to find a point on the plane, let's plug in, and let's not keep this complicated, let's plug in x is equal to 1 and y is equal to 1. And we're going to find the z value that corresponds to that. So we have 4x plus 2y plus z minus 16 equals 0. So 4 times 1 plus 2 times 1 plus z minus 16 equals 0. So 4 plus 2 plus z minus 16 equals 0. Let's bring the minus 16 to the right, so that's positive 16, and we have 6 on the left. 6 plus z, so subtract 6 from left and right, we have z equals 10. So therefore, 1, 1, 10 is a point on the plane. And again, any point will work here. Okay, so this just happens to be the point that we found. So 1, 1, 10. And the idea was, if you remember, we take some vector, so that'll be this vector here, from Q to P. So vector QP, we can just call that vector A. So vector A is just QP. If we take this vector and we project it onto the normal, the magnitude has to come out to be the magnitude of D, because D is going from the plane to that point, and vector A is going from the plane to that point, just in a different direction. All right, so overall, we see that D is going to be the magnitude of the projection of vector A on vector N. Now the formula for this, and what we saw last time, is the numerator becomes magnitude of n dot A, and the denominator is just magnitude of n. Now the dot product is a scalar, so the significance of having the magnitude in the numerator just tells us that it's going to be positive, and well, that's because distance has to be positive. All right, so n we have, or rather we can obtain, we have the equation of the plane here. Right, so we can obtain n. So n is going to be the coefficients of the equation. So there is the equation again right here, a little bit lower. So it's going to be 4, 2, 1. And to find vector A from the picture, remember that's QP. Right? So that's how I'm going to find it. vector A is QP, so that's OP minus OQ. Right, so OP, the vector going from the origin to point P, is just going to be 10, 3, minus 8 with square brackets, minus OQ, 1, 1, 10. All right, keep having to go up and down here. 10 minus 1 is 9, 3 minus 1 is 2, negative 8 minus 10 is negative 18. Okay, 9, 2 minus 18, so that's my vector A. So using A and N, I'm going to go ahead and plug it into the formula for projection and distance. All right, so N dot A, so that's going to be a vector dotted with a vector divided by the magnitude of another vector. All right, so here I have N, so 4, 2, 1, and that also goes on the denominator, 4, 2, 1. A goes on the right, 9, 2, minus 18. All right, so in the numerator, I'm going to have 4 times 9 plus 2 times 2 plus 1 times negative 18 divided by magnitude of a single vector. That's going to be the square root of the sum of the squares of the individual dimensions. So 9 times 4 is 36, 2 times 2 is 4, negative 18 times 1 is negative 18. And the bottom we have 4 squared, that's 16. 16 plus 2 squared, which is 4, that's 20, and then plus 1 is 21. So divided by root 21. 36 plus 4, that's 40, minus 18 is 22. 22 over root 21. I just like getting it in exact form before I fully compute it. And so that becomes 4.8 units. That's approximate, right? Not exactly 4.8, but approximately 4.8 units is the distance. All right, so the distance between the plane and that point. Again, you have to find a point on the plane, and then using the point in space that you have, figure out a vector going from the point on the plane to the point in space. Take the vector between those 2 points and project it onto the normal vector. And however you project it, take the magnitude of that vector, it's going to become D. If you just took the projection itself, let me draw that in orange. If you just took the projection itself, it would be this vector D right there. But since you're taking the magnitude, it becomes the distance D. All right. We have one more piece. Okay. We have to find the distance between the plane 4x plus 2y plus z minus 16 equals 0 and the point B. So let me just rewrite the equation of the plane. 4x plus 2y plus z minus 16 equals 0. And we're dealing with the point B, 2, 2, 4. Same idea. The first thing you need to do is check to see if the point is on the plane already, because if it is, you're going to save yourself a lot of time. So here we go. So 4x plus 2y plus z minus 16 equals 0. So leaving blanks here for x, y, and z, minus 16. All right, so this would be left side, and we want the right side to equal 0. All right, so plugging in the points 2, 2, 4. So that means left side is equal to 4 times 2 is 8, 2 times 2 is 4, and then we have 4 again, minus 16. 8 and 4 is 12, plus 4 is 16, minus 16 is 0, which is equal to the right side. That's going to save us a lot of time. So since left side does not equal right side, therefore B is on the plane. Oh, sorry, it is equal. All right, since left side equals right side, B is on the plane. Therefore, the distance between the point and the plane is 0. Okay, and that is it for lesson 8.5. Okay, so stay tuned next time for the last video in this chapter, 8.6.